Thank you very much. So I've been asked to talk about databases and the cloud today, and so that's pretty much what I'll do. So it's a bit of a challenge because I think you guys have a very, very broad background, or kind of wide-ranging backgrounds. And so what I'll try to do is, the ultimate goal of today as well as tomorrow is kind of to give you an overview of data management, starting with a little bit of history, and then move on to kind of tell you and show you what has been happening in recent years, the trends to NoSQL, to large-scale data management, to scaling into the cloud, and so on. And so the goal kind of is, or what I'd like you to be able to do at the end of this, is really to understand a bit the data management or data processing landscape so that you can make good use of it. So kind of you understand what tools are out there and what they are good for. I'm going to start with a bit of history, trying to show the last couple of decades what has been happening in terms of data management. Then I'll go to NoSQL, recent developments, and we'll see how it goes in terms of time. I was also planning to talk a little bit about data privacy, and but that's probably going to happen tomorrow, time permitting. Simply because I think once we talk about data management in the cloud, data privacy is an important aspect. All right, so I wasted even more of your time now by explaining what we're going to do. Let's just do it, because I think we're a little late. So what has been happening in data management in the last couple of decades, I mean, the starting point for data management was banks. They needed to keep track of their customers, they needed to keep track of the account balances and so on, and back in the day they would just keep file cabinets with all this information at their branches, which of course became a kind of a limitation, a bottleneck once we introduced, or once customers became a bit more mobile, and also once cash machines became available. You couldn't just keep the balance of each customer in just one place. So you needed a bit of infrastructure that connects all this information together. And that's what a couple of decades ago, I think pretty much in the 60s, that's where data management kind of had its starting point, with the kind of the birth of the database, where really, I mean, driven by banks, information was organized and stored so that it is in one place, it's consistent, and it's remotely accessible. And from that came the relational database in the 60s already, the idea to organize structured schema-based data. I'm not sure who is familiar with SQL or relational databases. Who has ever written an SQL query in here? That's a couple of people, I'd say. That's very good. So, yeah. So the basic idea really is to structure the data and allow to kind of structure it into tables and allow for efficient querying of this information. And that works really, really very well if you have structured data, if you have things like accounts, if you have things like customers with clearly defined attributes and so on. That works really well. And so what we do in the relational databases, or kind of SQL systems, is we store things, data, in databases, and then we query it with SQL, the general purpose query language, right? And when we want to do information, we store it in different tables, and we want to put it together, we join these tables, which is a fundamental operation in relational data management. And one really important point is that for decades, development of relational databases has been focusing on strong consistency. That essentially means that we want to make sure that the balance in the account of every customer is correct, right? Because that's something you really want to, that we really want to make sure that it's correct. So one important concept that is inherent, that was inherent in the development of relational database, was the concept of transactions. The idea that if we have two different people accessing the same data, the account balance, for example, we might end up with a race condition, right? So this example here shows a concurrent access on a common account. John and Jane are accessing this account at the same time. They want to withdraw $50 and $100. They first get the balance, they check the balance. If it's bigger than 50 and 100, they deduce the $50 and $100 they want to take, and then they update the balance. So the question is, if the initial balance is $300, what will the final balance be? Can anybody tell me? It's a trick question. Exactly, it depends on the order of execution. And that's something that we can't really, there we really need to have a mechanism that ensures that we get a consistent result in the end. Right, so what has been developed over the last couple of decades was really an important aspect of relational databases is this notion of transactions. Another aspect, another important construct in databases is indexing or the efficient retrieval of data, right? If we want to find one account with a balance of 920, what can we do? We can go through the entire table of accounts, of entire table of customers, which may be very slow if you have a large table, a large database. Or what we can also do is use auxiliary data structures like indexes, right? So this, for example, here is an index, a B tree, it's called, that structures or has pointers into the table. So if we, for example, if we start at the root, we say we're looking for an account with a value of the balance of 920. The root has a value of 800. We go on this side here, we see it's 900. This is, or we basically have three ranges here: smaller than 900, between 900 and 950, or bigger than 950. And so we go to this child here, and this will then point directly to the account in the table with a balance of 920. And so that accelerates lookup considerably. So that's those are the constructs that have been developed over years, and databases have been developed around them. Back in the day, I say a couple of years ago, we primarily had database systems that were shaped or developed for these online transactions, banking applications, you're making sure that we have a consistent result in the database, as well as business intelligence, kind of a larger scale analysis of business data. Now, what has been happening is quite a paradigm shift. We have new applications these days, web applications and scientific applications, and those are not really served well anymore by current relational database systems, I should say. What has also changed is that we used to have a very simple model. We had a processor, memory, and a disk. That's what the database system runs on. Today, we have much bigger deployments. We have changing hardware. We have new technology. We have SSD, flash technology. We have multi-core processors. And also, like this image here illustrates, we're scaling out into the cloud. We use huge number of machines to compute things in parallel, do data analysis in parallel. And so a few years back, the database research community, as well as industry, of course, came to the conclusion that relational databases are no longer fit for purpose, in the sense that things like I just said, right, they changed, new applications, different hardware, underlying hardware to run on. And so a couple of limitations were identified. So for example, one is this whole notion of transactions is great for banking applications, but it makes it very difficult to run things in parallel to distribute transactions, right? And that inherently limits scalability. And some applications don't need consistency or transactions, right? Then, for those of you who have worked with relational databases, what you always have to do a priori is to define a schema. You have to define the tables that you're going to use. That's great. That means you have a nice contract with the database. You know exactly what you put in. You know exactly what you get back. But if your application changes, that schema evolution, changing the schema is non-trivial. Then another limitation is that there's little optimization for novel hardware, like I mentioned, flash technology, SSD, new types of disks, multi-cores, and so on. Furthermore, some people say that relational databases, that SQL is a cumbersome language. It's not entirely wrong. queries can become big and complicated, particularly for different purposes, right? And then finally, relational database today, or back in the day, had limited data types. Very simple data types, nothing complex. And a lot of the times, when you had an application that was storing data in the database, you had to transform the data in order to store it in there, get it back, transform it again. It's all very complicated and, strictly speaking, unnecessary. And from that basically came the idea of developing this new notion of NoSQL. And so the idea is that we scale much easier, so we get rid of the consistency issue, right, of the transactions. Because we can't simply turn them off in relational databases. They are inherently designed into SQL databases, and that limits their scalability. So with this new kind of trend to NoSQL, we want to have, we do away with the consistency, because a lot of web applications don't need consistency or transactions. Transactions are important, are really important when we're talking about balances, bank accounts. But we talk about likes on Facebook. You know, if one of them gets lost, it's probably not the end of the world, right? So web applications don't really need them, and they don't scale very well because of them. So we give up the consistency. I think I made that point, right? Or some of the consistency at least. And then we put in a very simple interface, do away with the complex language, and use essentially you know, a simple interface with put and get and similar operations. I'll talk about this in more detail. All right. So there comes, you know, kind of this trend towards NoSQL and NewSQL. I'll talk about what the difference is. As always, you know, this is NewSQL. NoSQL is a bit of business talk, business buzzwords, and its definitions are not entirely clear, at least not on a technical level. I'll try to make it as clear as possible, at least reflecting my opinion. So NoSQL really is the idea of not only SQL or not relational. Has 6 key features. Scale horizontally, meaning we scale out into the cloud. What that means, I'll talk about later a bit more, right? But we want to enable scalability for large-scale applications. Then we replicate and distribute the data over several servers, such that we don't have everything in one place, such that we don't have one bottleneck. And then we use a simple interface to that. We also have, like I said before, we remove this issue of transactions and consistency. We have a much softer or much weaker model for that. And we also use main memory as a means to accelerate operations, because disk simply is a bit slow today. And then finally, a flexible schema, so that when the application changes, we don't have to redesign the whole database schema, which is a slow and tedious process. And so what that gives us essentially is a kind of this NoSQL, the idea of NoSQL, and that translates into a completely new data model. The old data model was we have tables with columns. Now what we have are tuples, which essentially are the same as a row in a relational database. We have documents in document databases. We have extensible records that we store, or objects that we store. It's kind of, we moved, the language has changed, the object or the things we store are more or less the same, they just have a bit of different attributes. Okay, so what I want to do now is talk a little bit, give you 3 examples of such systems, that you get so that you get a sense of what that actually means, right? So one of these systems, of these new NoSQL or class of systems, are key value stores. These are really more like a file system. They have a very, very simple interface. You just have essentially a lookup and insert, and that makes them very easily scalable. We can easily scale into cloud. We can distribute the state or the data on multiple servers, right? So for example, we have different tables in there, and instead of having different columns, we simply have we store key and value pairs, right? And we have a couple of operations on the API, but it's nothing nearly as sophisticated as SQL. But what we can do is we can insert a key and a value with the insert operation, and then essentially we can look it up, we give in the key and get the value back, right? And this we have a couple of more operations like look up for a key range, get next, and delete, and so on. But this makes it very simple, and if an application doesn't need the sophistication of relational database, you don't need SQL, this is a perfect solution to scale, because all you need to do is you just take this table, put it on one machine. If it doesn't fit on one machine, you put it on two machines, right? Because then you just send the key to all these machines and you get the result back. So this scales very, very well, right? Another NoSQL technology is document stores. The idea here is that we basically use, we don't store like we did in relational database, we don't store tuples. What we do is we store documents, and these are JSON documents. That's essentially a bit of a way to structure data. I'll make an example on the next slide. And so they allow us then to store this information and retrieve it again and have a little bit more complex queries on top of that. I think it's probably best to make an example here of what this query means, right? So what we're seeing here, basically, this bit here, let's see if this works. This bit here is, all of this is the JSON. Yeah, it doesn't work as well. This is a JSON document essentially, and this has the structure of a first name with John, the last name with Doe, and an age of 39. And these brackets and the commas and the double columns and the quotes, these are all kind of formatting, right? The essential bit that we want to store is this JSON document here. That's all we do, right? We tell document store, in this case it's an example with MongoDB. We say insert this JSON document. We could use any other type of JSON document here. It's just about storing this information. We want to store information about John Doe. What we can then do is query again for the same information, right? And we do this again with a JSON document. This one is much simpler. And we execute on the database find, and we put in this JSON document with the first name being John, right? And then it gets us back this JSON document as a result. We can also update documents in document stores, right? And the way we do this is we say we have one JSON document that identifies the documents that we want to update, and then we say what we want to do on these documents. And then finally we can also remove, right? What's nice about this is that we can insert whatever we want in this document database. We can add, for example, we can add somebody else with different attributes and so on. So it gives us this idea of a flexible schema, which can be really useful if your application evolves quite fast. Then we can easily adapt to that and change the schema easily, right? The other nice thing about this is that a lot of data today in web applications is either in XML, is somehow structured, or is even in JSON, right? And that makes it in this JSON format with the curly brackets and so on. So that makes it very easy to get the data from the web app, put it in this document store, and get it out again. What we had to do before with the relational databases, we had to go, if we get this piece of information here, this document from a web application, we had to parse it, we had to get the first name out, the last name out, and put it in the database. When we get it back from the database, we had to put it in this format again. It's a lot of overhead for not much use. So that makes it kind of really, so there's two really good points about this type of database, about this document store. One, we have a flexible schema that we can just change on the go. And the other is we already have everything natively stored in JSON. And that kind of answers to this limitation of relational databases that don't properly store or don't properly support more interesting data types. It's not all good, however, and this is a point I like to make about document databases. it's great to have this flexibility, but what it allows us to do is to insert really documents of completely different structure or somewhat different structure. In this example here, we're inserting 2 vacuum cleaners. Not sure why I made this example with vacuum cleaners. But in one case, we basically say everything about it, right? The model number and so on. We store the stock as well, the category, which is wrong, but doesn't matter. And in the other case, we store the same basic information, but we store the color with it, right? And so the problem then is, or what do we actually retrieve when we retrieve for the category vacuum cleaner with this query here? Of course, it's going to be both of them. We won't know what exact attributes these 2 documents have, right? So we'll have to, the problem then becomes that the application has to check for what attributes are actually available. And then so you're pushing a bit of the complexity out of the database into the application. And that can make it a bit cumbersome, right? Whereas with relational databases, you have a clear contract between application and database. You know exactly the structure of what you're getting back when you query. The semantics, what is in the database, may be rubbish, but at least you have the structure, which is something you don't have here. So these are the 2 examples I wanted to make about NoSQL. I want to move on to NewSQL, which, you know, like I said before, there is, I think the distinction between the 2 is somewhat difficult to make. But my attempt is essentially this, that we say NewSQL are scalable relational systems. And one really big issue about relational databases is they don't scale very well, you know, when you want to go on multiple machines. The issue being that you need distributed transactions, and transactions essentially mean you need to acquire locks on certain pieces of the data remotely, and if you do this distributed, it becomes a bit of a mess and just basically doesn't scale very well anymore. And so the idea of NewSQL is to make these systems scalable by dropping transactions altogether. That's one approach, which is fairly simple, right? Or then to make them more efficient by doing so in main memory or on new storage hardware, essentially. So it's kind of a weaker form of relational databases, but this is important for certain applications that need the structure of, or that want to deal with structured data, where relational databases are great but don't need the transactions. Then these NewSQL systems, where you need a lot of throughput, are very, very, very good. Okay, so that's kind of the distinction between NewSQL and NoSQL. Like I said, it's sometimes hard to draw a proper line there. What I want to do now is talk a bit more about actually what I'm supposed to talk about, which is databases and the cloud. And this is what I want to talk about here is MapReduce primarily, or the cloud and MapReduce, because MapReduce offers a really nice abstraction to do data processing or data management in the cloud on the large scale. And this is supposed to serve for you as kind of a way to understand MapReduce and also maybe see a little bit the potential that this could have for your work. So MapReduce, who has ever heard of MapReduce? That's too many. There's no point for me to... Shall we wrap it up? No, all right. So basically the idea of MapReduce is to scale data operations into the cloud on multiple machines, right? The typical large data problem is that you iterate over a large number of records, over a large amounts of data. There's something interesting in each piece of them. So, but what's important is that you can do this very, very easily distributed, because every part of this problem can be solved in parallel. Every part is kind of independent of each other. And so the problem becomes, how can we do this on the large scale? How can we solve a large data problem, right? I kind of given already the solution. But the idea is to use a large number of cheap off-the-shelf computers to do so in parallel. This works really, really well because, like I said, many of these large-scale data problems can be easily parallelized, right? And what has helped MapReduce has been around for quite a while now. What has tremendously helped MapReduce is the emergence of cloud computing. I squeezed in this slide, the next slide here about cloud computing. I suspect most of you guys know what cloud computing is. I still wanted to put the slide there because it says it in the title of my talk, cloud computing. I felt I need to have at least one slide about it. But it's really important. I mean, cloud computing is really important. Without the idea of cloud computing, I don't think there would have been any kind of MapReduce, right, or MapReduce type of systems. And what cloud computing essentially is, I like to call it utility computing, in that you can rent easily, or you get IT infrastructure or virtual machines or computers as a service. You can easily rent them on a large scale. You can rent them today for a few hours. You can just do this, and you get massive number of computers. You don't really care where they are. You just rent, or you just request them, and you get them quite easily. And there's a number of providers of cloud services. Amazon being one of them, Microsoft now with Azure, and I need to plug here Microsoft because they've been very, very kind to me in offering for my courses cloud resources. Google also offers cloud, or also has cloud offerings. Now, the basic idea now of tackling one of these large-scale data problems is the strategy of divide and conquer. And that's not something fundamentally new, right? I suspect most of you have a good idea what's going to happen now. So we have a piece of work, right? We want to analyze that. We want to do something on that. We split it in a bunch of, well, parts. We partitions the work. Then we have a worker working on each one of them. They produce a result on each one of these partitions. And then finally, we get the result together. And that gives us two phases, right? We have a partition phase as well as a combination phase. The partition phase, the partition entire set of data. The workers working them, results being combined in the end. And what's important here really is this, what I call, and what I think most people call, this kind of embarrassingly parallel aspect of the problem, in the sense that we can easily partition the work. Each worker can work on it independently. There's no communication between these workers necessary. And that means that, you know, we can scale this out to hundreds or thousands of machines. And the idea here being really, and I'm probably jumping ahead a little bit, but, you know, each machine in the cloud deployment runs one of these workers and processes one of these partitions, right? That's the basic idea. So, sounds simple, but there are a number of issues that we need to address, right? We want to parallelize this problem. We want to take the different partitions and have the workers work on them. How do we do that? So there's a lot of questions here. How do you assign workers or work to workers, right? What if you have more work units or partitions than workers? That one's probably pretty simple in the sense that every worker will probably take several work partitions. What if workers need to share partial results? How do we aggregate partial results? How do we know all the works are finished? And finally, and that's really something I personally felt the pain of, is what if a worker fails? You know, I started my PhD on working on distributed problems, and this was on a cluster of computers. I don't know how many there were, probably 64. Every time I run an experiment, some of these workers or some of these machines will fail. And there was basically the question, do we buy a new cluster or do I change my PhD subject, right? I went for the latter, which was the right decision in many ways. Anyway, so the question is, how can we organize these workers together and distribute the work, right? because this is difficult. We don't know in which order things work. We don't know when workers interrupt each other. We don't know when they access the data. We don't know where the data is. We don't know how to ship the data to the workers. And we need some sort of synchronization. That means there can be deadlocks, live logs, race conditions. It's just making it very, very difficult. And it's actually something that we don't want to put on the programmer, right? Because we don't want the developer to have to deal with all these kind of problems. So how can we solve or address this issue? How can we get to this idea? The really important bit is to develop or to come up with the right level of abstraction so that we can take a problem, think about it, on how we can easily parallelize that. So that kind of leads already to the MapReduce paradigm that really makes you think about how can we, looking at a problem, how can we parallelize that easily? And then also, what we want to do is hide the system level details from the programmer, right? We don't want to have the programmer or the developer deal with all these issues of failing workers and so on. And then finally, what we want to do is we want to separate the what from the how. And this is really important. This is quite a nice aspect also. I like to stress that when I talk about MapReduce and Hadoop and all the rest of it. This is very similar to SQL and declarative languages, because with SQL you don't tell the database how to retrieve the data. You primarily tell it what you want, and you leave everything else to the database. And the database actually does that. It decides how to efficiently retrieve the data that you want. And the same here. So we need something, an abstraction that allows to tell the system what you want and not necessarily how you want it. There's always going to be a little element of how you want to do it in there, but you will have to focus primarily on what you want. And so the key ideas with MapReduce or Hadoop are essentially to scale out and not up. Scale out means we add more machines to the problem. Scale up means we add more resources on a single machine, right? And with scaling out, we can go into the cloud, we can go to cheap resources, but very, very scalable. Another aspect is that we're dealing with large amounts of data, right? And moving them around is painful because bandwidth is limited. And so what we do in this case is generally we move the code to the data instead of the data to the code, right? Data is somewhere in the network, somewhere in the cloud. We just move the computation there. Other things that we want to do is we want to process data sequentially because a random access, particularly on disk, is quite costly. And with that in mind, a few years back, this idea of MapReduce was developed. Now at this point, it's probably useful for me to say, because I can't keep on mixing these two things, Hadoop and MapReduce. MapReduce is basically the origin. Google came up with MapReduce to do certain analytics on their data. They never released it into open source, and so Apache or some developers came up, basically implemented Hadoop. By and large, these two things are the same, comparable, and because they're basically the same, I tend to kind of mix them up a little bit. But it's the same thing for all intents and purposes. And so Hadoop or MapReduce is a scalable fault-tolerant system for large-scale analysis of data. And people have done crazy things with it in the sense that, and I'm going to talk about this, time permitting, I want to talk a little bit about this, because people have been implementing databases on Hadoop, on top of Hadoop. They've been implementing workflow systems on top of Hadoop. But it really makes it nice because you can really do all of these tasks that you already were able to do before. You can do them on a really large scale now in the cloud. Okay. And the idea really is, I said it before, we want to have as simple as possible an abstraction that allows people, developers, to parallelize these problems. And the way this works is that we have two basic functions. map function and the reduce function. Both of them work on key value pairs. Key value pairs is the abstraction, the organization of data used in MapReduce. And so we have these two functions. Map basically takes in key value pairs and produces new key value pairs, and reduce takes in key value pairs and then produces again key value pairs. Now that I said this out loud, I realize I basically do the same thing. They take key value pairs and produce key value pairs. But the point, one important bit is that reduce operations get all the key value pairs with the same key. And that's very useful. And then the execution framework handles everything else. That's a pretty convenient solution, right? So, and the reason why this is useful is that the key observation from analytics algorithms is that they actually typically have a common loop that works on all the data instances. So this is what I try to do here is illustrate this. So we do for all data instances, for all partitions of the data, we do some processing, and that's exactly what MapReduce can help us with, right? So the idea really is that we have two functions, map and reduce. Map takes as input any kind of data, key value pairs, or also other data, produces other key value pairs, right? So we have the key value pairs, the input data at the beginning. We feed this into the mappers. The mappers will then produce key value pairs. In this case, this mapper here produces key value pairs with the key A and the value 1, a key B and the value 2, right? And so on. Those are then being redistributed through the whole cloud deployment. They get combined. All key value pairs with the same key are combined in the sense and are then sent on to the reducers, who will then produce the final result, right? Now, this is going to be a lot more data than just 6 key value pairs, of course, right? These mappers will work on a cloud deployment for, I think it's simplest to assume that each mapper is going to run on a different machine to make the problem really scalable. Then in the middle here, we'll use the network to distribute the key value pairs to the reducers. And also here it's safe to assume that each reducer is running on one machine. One can combine these things. One could say, I'm going to run all mappers on one machine. I'm going to run 3 mappers on one machine and 2 mappers on the same machine and so on. Well, I think it's safest or easiest to assume that that every mapper and every reducer runs on one machine to truly enable scalability. And so what's also interesting here is, for example, if we have a mapper like this one here, it will produce an output key value pairs that are going to be stored locally, for example. And now if we want to work on this key value pair, right, instead of sending these key value pairs around to the next reducer that needs them, what we can also do to a certain extent is kind of move or execute the reducer on the same machine so that the data is local. That's kind of the idea of moving the code to the data instead of moving the data to the code. All right, so this is basically it, right? What we have to do is we have to implement a map function and the reduce function that does the work. I'm going to make, I think, at least one kind of more, one example that illustrates this a bit. What I want to talk about before, however, is that sentence here, right? The execution framework handles everything else. What does that actually mean? Because we have all these kind of issues, I mentioned them before. We have kind of like we need to distribute the data, we need to shuffle data around. And so that's what MapReduce does for us. It handles scheduling. It assigns workers to map and reduce tasks. It moves around the data if needed. Like I said before, we can also move around the code. It handles synchronization. It waits for all the mappers to finish before it starts the reducer phase, generally speaking. And most importantly, it handles errors and faults. So if a worker fails or is working too slow, it's going to give the work to a different worker or to a different mapper or reducer in order to not delay the overall result, right? So that's what the MapReduce runtime is doing for us. And so really all we need to do is define the mapper and the reducer. Okay. And so, like I said, we have a MapReducer, we have a map piece of code we need for the map, and we have a piece of code we need for the reduce. And that's it, which is not entirely true. We can further optimize things by implementing also these two, by also providing these two pieces of code for partition and combine. I just want to mention combine because I think it's kind of shows an interesting optimization on how MapReduce works. So if you have the same example as before, right, what we have now is we have these combiners and partition, and what this combine does essentially, and we need to write the code for that as well, is if we have a mapper with similar key value pairs or with key values pairs with the same key, then you can already combine that locally before it sends it on the reducer. That reduces a bit the network traffic, right? Here we have 6 key value pairs. Won't make a difference here, but if you have hundreds of thousands, millions or billions of key value pairs, then an idea like a combiner will make a difference, right? This will send it on just as instead of C3 and C6, this will send it on as C9. And then it will combine it at the reducer. It will arrive at the reducer also combined. So this C9 will pop up here, right? And that's a small optimization. Of course, we need to tell the combiner, we need to implement the combiner and say exactly how to add up, how to combine the key value pairs. Okay, now on to an example. This is essentially how one can implement this idea, an example, a mapper and a reducer example. This is the usual example made with MapReduce, which is the example of a word count. You essentially have an input document, no matter how big it is, and you want to count the frequency of words. What you do is you implement the mapper, takes the document, essentially takes a document or a piece of the document. Each mapper will take a piece of the document and will iterate through all the words. For each word in the text, it will generate a key value pair with the word as the key and the value as 1, right? Because essentially each of the words, or every word it sees, has an occurrence of 1, as far as I can tell. Then all the key value pairs with the same key will be sent to the same reducer. So each word will be each single word, all instances of it, all key value pairs of it will arrive at the same reducer. And all the reducer then has to do is, for each value, it simply adds this up and then generates in the end a key value pair with the word as the key and the total occurrence of this word as the value. And that's essentially how we can count words in a really, really large document. It's an example which is supposed to illustrate MapReduce. It's not supposed to be particularly useful. But what I want to say is, it's just here to really kind of show how this works. And then, one can build on this simple principle of these key value pairs that go through mappers and reducers. One can really build powerful applications that I will talk about later on. Okay, yes. So like I said before already, Google has come up with the whole idea of MapReduce. Since then they have moved on, but they have never really open sourced it or made it available to people. They published it in papers, and so people took these papers and implemented it as an open source piece called Hadoop. It was first done by Yahoo, and it's used in a lot of applications and a lot of companies, this is supposed to be a list of them. I want to highlight one example that I find very nice and illustrative, which is one of the New York Times. They, at least in the past, so what they had to do every night is they had to reformat the images they use for the newspaper, for the online version of the newspaper, right? They took a high resolution image and then just generated a couple of them for each. They generated one for mobile devices with very low resolution and kind of reasonable resolution for mobile for laptops and so on. So they had to basically rescale and change the format of a lot of images every night. Now, of course, one option is simply to just go and buy a huge cluster, but that would basically be idle throughout the day, right? So what they chose to do is just use kind of cloud computing resources. I think they were using Amazon, I'm not entirely sure. They went to Amazon and every night they would rent a couple of machines, use MapReduce to do that, right? And you can easily abstract it because you have tons of images, thousands of images, well, hundreds or thousands of images, and you can resize and rescale them in parallel. You can work on each image in parallel. It's absolutely no issue. And so kind of they could offload their peak demand into the cloud using MapReduce, which is really a lovely application of this principle, right? It's fair to say there's other ways of doing this. They could have developed their own application, complicated, takes a lot of time and resources, and it's probably not that useful. But they built it in MapReduce, simple level of abstraction, and very scalable. Now I think, yes, this is the final example yet. Again, the word count example with actual words to make it a bit easier to understand. So what we have, again, is the same principle, right? We have as input, we have different pieces of text from a big, document. We send each of them to a mapper, which goes over each of the words in the text that it's actually dealing with, produces these key value pairs here. The occurs once, brown occurs once, and fox occurs once, and then also quick occurs once, right? It sends this through the network, or the reducers are moved to the data, and each reducer with the same receives the same key value pairs with the same key, right? So this reducer here gets brown, fox, how, now, and the. And actually these are the only interesting ones, really, the fox and brown, because only those occur twice, right? Brown, I think, is coming from this piece of text, from this mapper here, and from this one here. They all go to the same reducer, and then it outputs these key value pairs. And we have a total count of words in the text. So anyway, so I want to give a bit of an overview over NoSQL systems, and even, I'm kind of summarizing stuff that I haven't talked about and I might talk about tomorrow. But what I want to kind of really show is a bit of an overview, right? So we have all these NoSQL systems. We have key value stores. There's one available. Really, they have this, like I said a little while ago, have this kind of key value abstraction. You basically, well, this is my address actually. This is, you store a key along with a value, and that means you can only retrieve based on this key again, which is sufficient for a lot of applications. One system there is this Cassandra. What we've seen is document stores. I've made the examples with MongoDB. There's more available. There's also CouchDB. Personally, I prefer MongoDB because it's a bit easier interface. We have these scalable SQL systems. One of them is VaultDB, which I haven't talked about too much. This is what I would say a new SQL system in the sense that it runs in main memory. And then we finally have the data processing system, one example here being Spark, as well as Hadoop, right? And Spark that I might talk about tomorrow. So what I want to, the one slide I really kind of want to show is this one here, which is the data management landscape, which is supposed to give you one perspective on all these products, and there are many more, right? I haven't, not by any means, mentioned all of them, right? But I just want to give you a few pointers in this space, because there's so many products with so many funny names these days, right? So yeah, so this is one way of looking at this. I basically, what I've done here is I looked at the query or analysis frequency as well as the structuredness, right? And this is, you know, my general approach to this NewSQL and NoSQL trend is that this is not something that replaces relational databases, by no means. And some people look at it like this and it drives me nuts, because this is not, these are new points in the design space, right? For example, we have a lot, these days we have a lot more data that is unstructured. By all means, if your data is unstructured, use a database for unstructured data. Don't use a relational database. But I've been sitting through presentations where people went like, yeah, I had this relational database with voter data, for example, and it wasn't running fast enough. So I put it in document store and it was much faster. It makes no sense at all, because you know, you haven't optimized a relational database. You haven't kind of got the performance out of it that you potentially can. So one aspect, one dimension in this problem is the structuredness of the data, right? And it's really true. If you have unstructured data, by all means go for something that doesn't really need structure. If you have highly structured data, banking data, voting data, customer data, go for a relational database. But I'm going to fill this slide now. So one thing, so for me, the way I see this is, if you have a problem where you have very, very unstructured data, use something like Hadoop, right? This is going to give you not much performance, but you're going to be able to solve it on a large scale. And you're going to have to, because your data is unstructured, you're going to have to write your own MapReduce, of course, right? You're going to put the parsing, the kind of reading of the data in the map of the reducer, and then you can do this on a really large scale. So this works very well. If, however, your data is very unstructured, but you're going to run the analysis 1,000,000 times on this data, it's totally worth to take the data, get into a relational format, put it in the database, and then run your analysis on that, right? The next kind of system I want to mention is Spark. Is kind of similar in the sense that it also works on unstructured data. It is an optimization for main memory, meaning that it will run a bit faster. So here, if you know, depending on if you need to run your analysis a bit more frequently, by all means go for Spark. These days, most people go for Spark anyway. Hadoop isn't that fashionable anymore. It's probably really about fashionable. There's no really good underlying reason for it. Then, if you move a little bit up, if you have a problem that's a bit more, you have a bit more structured data, right? I mean, for Hadoop, this can be, the data you use can be anything. Can be like in New York Times, can be images, can be really anything that you can parse that you need in your application. If you have a bit more structure, go for something like a document database. You still have a bit of, like I said, with this schema flexibility. You can still change your schema on the go. You can still, you know, it doesn't have to be as structured as a relational database, but it's going to be a bit faster because it has a couple of optimization techniques built in, like also indexes. If you have even a bit more structured data, simple data, go for something like Cassandra, a key value store, provided you really only need the simple access of key and value, right? If you only need key value pairs to access them, then that's certainly a good thing to use. Then comes kind of the traditional space of you have a high analysis frequency as well as a very well structured data. Then go for any of the relational databases I just listed: Oracle, MySQL, and Postgres. probably should have listed Microsoft as well. But this is a case for your traditional databases. And then lastly, the one I haven't really talked about too much is kind of a new SQL solution, this VaultDB. The idea here, this is a system that works, it's basically a relational database management system that works in main memory, that makes it very efficient and very fast. And so if you have highly structured data and you do run a lot of transactions, you run a lot of analysis, then this is, it's also available as open source, then this is something to use. So the point here really is that depending on your problem, choose a solution, right? And this, like I said, these are two different, I chose these axes, right? This is a multi-dimensional problem. I could have chosen this axis as something different. You know, basically also the scale of your problem varies, right? If you have a really, I could probably come up with a couple of slides like this, and maybe I should. You know, basically, if you could also have on this axis here something like size of the problem, and then Hadoop and Spark very quickly become your only solutions. All right. Are there any more questions I have slides for? No? What I would suggest is I finish here, and then I'll continue tomorrow talking about this. And tomorrow I want to go a little bit more into kind of also talk a little bit about the Human Brain Project, how data management is used there, as well as other topics. Yeah, that's what I'll do tomorrow. Okay? Thank you very much.